Hello, and welcome to today's webcast titled Universal Storage for Fast Access to All Data at the Edge. My name is John McHale, EVP and Group Editorial Director with Military Embedded Systems Magazine and moderator for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speakers today are David Freeman, Senior Product Manager for the Sensor Systems Division at Mercury Systems, and Randy Hayes, Vice President for the Public Sector at Vast Data Federal. This webcast is sponsored by Mercury Systems, and the event is hosted by Military Embedded Systems Online and Open Systems Media. Before we begin, I have some short housekeeping items to go over with you. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will consume about 40 to 45 minutes, leaving the remaining time for the question and answer session. You'll find on your console window an area where you can enter questions in real time. We encourage you to ask questions throughout the webcast while this question is still fresh in your mind, and we'll address as many questions as we can during the closing Q&A. If you have a question for a specific speaker, please note so at the beginning of your question, or I'll just offer the question to both speakers. If you have a question pertaining to the webcast operation itself, one of our technicians will get back to you during the webcast. And please note, as much as we'd like to, we may not get to all of your questions today. In that case, someone will get back to you after the webcast with more information. On the console, please take note of the handout section. That's where you can find the slides being presented today, as well as other resources from Mercury and Vast. There's also a poll section where you can provide direct feedback on today's event. We encourage you to participate. This webcast will be archived online. The URL shown on your screen will be available within 48 hours. Once up, it'll be available for 1 year. Now I'm going to get us started with some key market drivers and why I think today's webcast and topic is so example of what's going on in the world of defense technology in the U.S. and also why it's important. From a market perspective, there's a tremendous amount of funding going towards sensor systems like C4ISR, where you see, according to Technavio, they expect that to grow to 2025 to 30.22 billion. It's hot. The DoD EW market, electronic warfare, is also set to reach 3.6 billion by 2025, according to Frost and Sullivan. And all that funding is creating a huge demand for data, more and more data. And that's where technologies like or technology applications like big data, where it's processing, filtering, and storing all of that sensor data that comes through. A lot of that tends to embrace artificial intelligence solutions. And at the end of the day, to make this stuff happen within the DoD, they're leveraging commercial innovation. And it's become very critical to do that because 30, 40 years ago, when the DoD was the driver of all technology, now they're a consumer just like you and me. And so, and I also think about it from a sensor chain perspective. We're talking about sensor data. And I kind of, full disclosure, I stole this from an old sensor chain idea that Mercury had a few years ago. But if you take a look at this chain, it starts with data acquisition, typically at the sensor, data digitization, data processing, then the storage of that data, and how do you access that data quickly, and how do you act on it? And we're going to talk about those two items that are bold-faced today from our experts over here. David and Randy are going to go into much detail on that. And then looking at this and looking at some of the other events I've seen this year, this was a quote from last year from Deputy Defense Secretary Dr. Kathleen Hicks about where they're driving their acquisition. And I think it's very apropos to what we're talking about and what we see a lot in our magazine and our articles and what we talk to our readers about. Acquisitions of new technology should increase warfighting effectiveness, enhance resilience, leverage commercial technology and innovation, and rapidly respond to future threats. That part about leveraging commercial technology isn't just going off and buying stuff at Best Buy, right? You have to have companies, and typically these are third-party suppliers. In the past, they called COT suppliers or suppliers of rugged equipment, rugged technology, but companies like Mercury Systems that will take that commercial technology, whether it's the storage solution from Vast, maybe it's the NVIDIA or Intel processing chips, and make them work for defense applications. That's the secret sauce, and that's what you're going to hear about now. And so without further ado, I'm going to turn it over to Randy to tell you about that commercial technology innovation.
Great. Thanks, John. So, it's really interesting when I look back over the years working at Vast and working with a lot of our federal customers. We really set out to build a product that was going to support lots and lots of different applications and candidly to solve a fundamental challenge with storage. And, people have looked at storage for a long time as having multiple tiers of storage. There's really no value in tiering your data other than cost savings. And so if you can solve the cost problem of kind of an all flash file and object storage system, you can collapse down a lot of complexity in the data center and at the edge from a processing capability, from a storage capability, from an application perspective, from an ease of use perspective. Less tiers, less infrastructure, less things to manage is really what we set out to solve. I mean, people have been making trade-offs of moving and trying to pick different types of data storage systems depending on cost and performance, and you're constantly making these trade-offs. And so we really took a step back and said, hey, how do we solve really all these problems that people have had around storage for a really long time? And so when we did that, we really looked at, and it fundamentally became a problem of scale and a problem of the cost of flash. And so we basically set out to build an exabyte file and object storage system that was completely built on flash. And what was really interesting is then when we took a step back and we look at all the things that we've built into the software that we sell, is it really lends itself to this swap capability or space, weight, and power. And so when we went out to build this architecture and we take a step back, it's built for swap optimized environments. And I'll kind of walk through the architecture and kind of, how do we solve a lot of the traditional storage challenges that you see in the data center, but also at the edge, because these problems compound themselves when you have people that you don't have as many people to manage systems like this. You have adverse locations where you can't, call somebody. You can't spin up a Zoom session or a WebEx session and troubleshoot things. So when you start looking at supportability at the edge, it becomes even more important. And so, when we built this architecture, we really built it for everything, right? If you look at that kind of pyramid or, the tiers of storage, when you can support all these different tiers of infrastructure with a single platform, you also have to be able to support all of the different applications that are going to be at this architecture. And so now you have a single monolithic platform that can support all of your applications inside the data center as well as at the tactical edge. And so, if you're looking at shipboard systems, these are basically floating data centers. They have home directories, they have backup requirements, they have logging requirements. When you start looking at the tactical edge requirements, you're doing synthetic aperture radar, you're doing RF data, ingest and manipulation, tactical edge command and control. And then one of the really interesting things that we've seen a really big uptick is packet capture and logging data at the edge. And so being able to ingest a lot of this data and then run applications against it. And so, I think one of the really interesting things that we've seen over the last couple of years is the value of data has grown exponentially, and having fast access to all of your data, not just some of your data, has really been king. And so if you start looking at, kind of AI and applications at a whole, the more data you throw at these applications and algorithms, the smarter the algorithms become. And, if you're looking at autonomous driving vehicles, you want to give these systems as many views of what could happen so that the autonomous systems can make the best decisions. And so that really comes to having fast access to all of your data. So we support a large number of backup, big data, AI applications, as well as enterprise infrastructure, whether it's Kubernetes, VMware, OpenShift, OpenStack. We have the ability to support a lot of these different types of platforms as well. So, a lot of people ask us, okay, how did you guys do this? Like, how do you solve all of these problems that have been plaguing the storage industry for a really long time? And so one of the really interesting pieces is we kind of took a step back and we made some forward bets on technologies that really weren't generally available until about 2018. One of those is NVMe over Fabrics. A lot of people think about NVMe and NVMe over Fabrics as a really fast host side connection. We actually don't use it like that at all. We use it as kind of a hyper interconnect, and it allows us to place data on the other side of the network and build an extremely scalable cluster architecture. The other thing that we use is QLC flash. A lot of people will think of this as hyperscale flash, is what a lot of the cloud vendors use, from a flash perspective. It's great. It's very dense, which obviously is very pertinent to swap optimized use cases. It's a very low cost form factor. And the read performance is exactly what a TLC or MLC flash device is. However, there's some challenges with QLC and hyperscale flash. One of these is you can't overwrite these devices very many times or you burn them out. And so we had to solve for that problem. And so one of the ways we solved that problem was with something called storage class memory. And if you're not familiar with storage class memory, it's basically faster than your traditional flash drive. However, the most important thing is it's non-volatile. And so if you talk to anybody that builds storage systems for a living, the two main reasons for data loss or data unavailability is cache coherency or destaging out of DRAM. And because we've pulled all of the volatile memory out of our write path from a storage system perspective, we don't have to worry about batteries or super caps or anything like that because we're writing data to a persistent media. And so again, this lends itself very well to these swap optimized type of use cases where power can be a little flaky, where shock and vibration could be an issue. And so we've built this storage system to solve a lot of the traditional data center problems that you would have. However, everything that we've built in this platform also lends itself extremely well to the swap optimized type of requirements where you're trying to solve space, weight, and power. And if you can solve those problems with software, that's even better. And so I think that's one of the great marriages that we've built with Mercury, is that we're a software company and we've built this around commodity hardware that Mercury can then ruggedize and layer our software on and build a turnkey appliance. So we take these three technologies and we put them together into our cluster architecture. So I know this is kind of a busy slide, so I'll kind of walk you through it and then we'll kind of discuss a couple other things that are really pertinent for space, weight, and power if you're going to forward deploy this equipment in a submarine or a boat or on a Humvee or on a plane. You're thinking about all these different architecture characteristics that we've built into the platform and how they work towards the swap optimized use cases. So at the bottom, we have these things that we call D boxes. They stand for data boxes. And so you can think of these as a big JBOF. So they're just a large chunk of flash as well as storage class memory. There's no logic that runs in these. You can think of this as kind of just the repository for all of the data. It's also the state of the file system. You could start with one. There's no single point of failure. So you can start with as little as one of these D boxes, and then you scale this out for as much capacity as you need. We cluster this all together with NVMe over fabrics, like I discussed on the last slide. This can be done over commodity Ethernet, like Rocky V2, or it can be done over InfiniBand with IB verbs. We do support both of those networking technologies, so you can ingest data via Ethernet, process data via InfiniBand, or vice versa. So we can give equal access to multiple different networks. And so on top of that, we built what we call C boxes for container boxes. And so what's unique about this architecture is these are basically Linux servers. And these Linux servers act as one part protocol server and one part global flash translation layer. And so what this allows us to do is scale performance by just adding low-cost Linux servers into the cluster architecture. And I mentioned that these are one part protocol server and one part global flash translation layer. Because they're a global flash translation layer, every single one of these servers that's running our software has equal access to every single storage class memory drive and every single hyperscale flash drive like it's direct attached. Why is this important? It's important because regardless of which one of these servers your clients connect to or your applications connect to, it can see the entire view of the namespace. And so every one of these servers can serve up every piece of metadata and every piece of data. And what that builds is an exponent of reliability, where you can lose every one of these servers except for one and still have access to all of your data in this architecture. So again, having this resilience built into the cluster architecture, again, lends itself very well to the swap optimized type use cases. From there, we're exporting standard NAS protocols. So we want a system that's easy to manage, easy to use, and most importantly, easy to deploy and support. And so it's a turnkey appliance. It shows up, it's configured, it's ready to go. We're supporting NFS over RDMA, which also supports GPU direct. So if you're doing any sort of sensor processing on a GPU, GPU direct allows you to bypass the CPU complex in your server and place data directly in that GPU from the network. So it increases performance and it lowers the run times of your applications in order to give you faster insights or faster answers to the questions that you might be asking. We also support SMB and S3. Everything's cross protocol. So you may have some sensor ingest that's coming across from like a Windows machine. So we'll support SMB. And then you could process that data via NFS, and then you could distribute that data via S3. And so S3 is very WAN friendly. So if you're going to move data across the WAN, S3 gives you a really good transport protocol in order to move data. And so having that cross-protocol range allows us to ingest data from multiple different sensors, multiple different inputs, if you will, and then allows us to process that same data in place on an all-flash file and object storage system. We also support a Kubernetes CSI driver. So if you have some Kubernetes clusters, we can act as a persistent volume for both Kubernetes as well as VMware, from that infrastructure perspective. So this gives you the ability to scale capacity independently of performance. So if you need more capacity, you're just scaling out D boxes. If you need more performance, you're just scaling out C boxes. So one of the really interesting things, and it just makes so much sense when you start looking at swap optimized, is we went and really set out to lower the cost of an all-flash storage system. And so we do that really with 3 different ways. But in the process of lowering the cost, we end up lowering the space, weight, and power consumed by these systems. And so one of the things that we do is we use QLC flash. We also support 10-year longevity for these flash devices. Nobody else in the industry supports QLC flash for 10 years. And one of the reasons that we've been able to do that is because of the algorithms that we've built on top of our file system. The other thing that we've built is something called a locally decodable erasure code. And then the last thing that we built is some really innovative algorithms around compression and being able to compress data that's historically not been compressible. And I'm going to kind of walk through each one of those and kind of how they relate back to, being in a space, weight, and power type of situation where you're trying to lower all of those things. If you think about erasure codes and kind of RAID schemas in the past, you really have something that was built on something called Reed-Solomon. And the general thesis around Reed-Solomon is if you lose a drive, you have to read from all the remaining drives in order to rebuild that failed drive. And we really didn't think that was a good idea, especially with the size of drives coming out. And so we went to academia and we found these things called locally decodable erasure codes. And so the locally decodable erasure codes allow us an erasure code schema that has a +4 parity multiplier, which gives us 60 million years of mean time before data loss. But the really cool thing is it's a fail in place architecture. So if a drive fails, we rebuild the data and only the data that was on that drive into free space, and then you're back up to full parity. And so if you're in a whether it's a boat or a submarine or a plane, like you can't be swapping drives, right? You're in a mission. You can't be swapping drives. And so with this architecture, the systems can fail, and it's a fail in place architecture. We rebuild the data into free space, and it allows us the ability to just keep trugging along. And so at the end of the mission, or at the end of a set time, you can then go and swap multiple drives out if you had any sort of failures. Now, the other nice thing about having an all flash system is flash just fails less than hard drives. Do they fail? Yes, at a much lower rate. But the fact that we're doing this locally decodable erasure codes, and the +4 parity actually acts as a force multiplier. So we only have to read from 1/4 of the drives in our erasure code stripe. The other really interesting thing is that the erasure code stripes grow as the system grows. And so the larger the system, the more resilient it becomes. And so it's a really interesting use case, and obviously helping out with these swap type use cases where you just can't swap drives in the field. And this gives you that ability where you really don't have to. So the other thing that we touched on was something called similarity-based data reduction. And so the way it works is data gets written into the system, we mirror it in the storage class memory, and then we acknowledge that write. So the writes are always fast and very low latent. However, because we're writing to persistent media, we have the luxury of time. So this data is now stored on storage class memory. And we could do some cool things with this data. One, we could build these really wide write stripes like we talked about for those erasure code schemas. But the other thing that we do is we hit the data with what's called a similarity hash. And it's not like a SHA-256 hash like you would see in an encryption engine. We're actually looking for hash collisions. For you computer science majors out there, it's called the nearest neighbor problem. It's kind of how Google image search works, or how the app, what's it called? Shazam. If you remember, you hold it up, you're like, oh yeah, that's Metallica 1, sweet, all right. And so it's the same thing, right? You're looking at data, you're looking for data that is algorithmically similar together, and then we group that into what we call similarity clusters. And then from there, we take a reference, and then we only keep the deltas off of that. And so this gives us the ability to compress data that's historically not been compressible. And so, to kind of put some, meat behind some of those claims, this is kind of a pretty neat slide. Is, compression is great. It's byte by byte, file by file, but it's local. You're typically doing it in a much smaller form. Dedupe is great, because you're globally looking at all your data, but you're looking for exact matches. So it's very coarse. And so typically you wouldn't run this on a big unstructured data set. There's just too much entropy in the data. And the last thing that we do with this similarity-based data reduction is we really boil it down to its smallest form factor. And this allows us to really drive, again, the space, weight, and power if we're getting multiples, right? So for a pre-compressed backup architecture, something that's already been compressed by something like a Cronus or Commvault or Veeam or somebody of that nature, we can compress that data again 3 to 1. For pre-compressed log files, if you're using like Elastic or Splunk, typically they will compress 2 to 1. We will compress an additional 3 to 1. So again, we're giving you more usable capacity because of the erasure code schema, but we're also giving you more effective capacity with this similarity-based data reduction technologies around that. And if I look at a cross-section of all of our customers, on average, we see about 2 to 1 compression. So now you're talking about, a 2U rack-mounted system that can hold 675 terabytes. And then if you're basically doubling that, I mean, what a better way to store more and more data than just being able to compress this data. Now, a lot of people are like, they call BS on our compression. And so we went to engineering and we're like, how do we convince people that, we can actually compress their data? And so we built this thing we call the probe. In case you haven't noticed, we have a lot of space theme with VAST. We actually call ourselves Vastronauts, as corny as that is. But we have this thing called the probe, and it basically, you give our software an NFS mount or a S3 bucket, and we can walk your specific data set and spit out a clear text log file that tells you exactly how much compression we will get on your specific data. And so it gives you a really good idea of kind of where we could be. With that said, we're a software company, so we rely on our partnerships from a technology perspective. And so, we've built some very creative software to solve a lot of these problems. We couldn't do it without other partners in the industry. And so whether it's, our use of Bluefield DPUs or Intel Solidigm Flash, or working with our great partners at Mercury. And so I wanted to hand the reins over to David, and he can walk you through some of the Mercury hardware platforms and some of the different things on that end as well.
Thanks, Randy. I appreciate it. It's going to be a tough act to follow, but I'll do my best. So Randy talked a lot about the software and how it works on the hardware, and the hardware and the software really work together. So we had to really come up with our hardware and tune it to make sure that it met what the hardware that VAST was already using, to make sure that you got the same benefits that the software provides. So Randy talked about the major components, and there are 3 major subcomponents. Here gives you a good idea of what they look like. So what you have at the top here is the D box, where all the storage is. And then in the middle, you have the switch box, where you have your Mellanox switches. And then the C box, where you have your processing. And that has the Xeon scalable processors in it, and there's 4 of those in there. So a little deeper dive into this. So this picture on the right here is of a D box. And the blue dotted lines show you where the E1L rulers are, the flash memory. And then in the middle here, the green is the U.2s, or the service class memory. Those are skids. There's 2 per skid or sled. And then at the bottom here is where the blue fields are, and this is where all the connections are. So this is in the orange dotted lines here. So this is a 19-inch rack mountable, 22-inch deep, swap friendly. To give you a comparison, the commercial version of this is over 30 inches deep. So at 22 inches, this fits, we feel, much better into the desired applications. Now, the redundancy is built into it. Between the D box, the C box, and the network, there's redundancy along with the power supplies. And we'll cover that in a following slide. Everything on here is front IO, front accessible. And the drives, to Randy's point, that if you do get a failure, if something happens, you need to remove them, it's right there in the front. You can pull the drives out and replace them with new ones. So easy access to that. It's been ruggedized. The system has been designed and tested to be rugged to the mil specs that every Mercury commercial hardware that we ruggedize is built to and designed to. So things like 810 shock and vibe, EMI 461, 167 naval vibration and shock. And then, of course, if you put this into a shock isolated 901 cabinet, you'll get very good performance out of it. It's been ruggedized to meet that. And then scalability. I know Randy, again, talked about the scalability, and we'll cover that in a slide and show you how we can do that in one of the following slides. So for the block diagram, you see the C box here at the top, the switch box in the middle, and the D box at the bottom. You note in the C box, there's 4 C nodes. Each one of those is connected to a network interface card. And then the switch box, you have your dual redundant switches. You see the interconnects between the switches, and then the interconnects up to the C box. And then in the D box, there's 2 D nodes. So if one of these were to fail, the D node or a switch or a C node, you still have access to all of that data, and the system will still run. What we did is we tried to provide some standard configurations as starting points. And what we showed you originally was the 1x1, which was a baseline configuration. Again, 1 D box, 1 switch, and 1 C box. Here's a standard configuration where we've added another C box and another D box to give you twice as much performance and twice as much capacity. In this instance here, by just adding a single D box, you're able to add more capacity. And in this configuration, the one on the far right, you're adding a C box, which doubles the performance capabilities out of that. And then we have a chart here, and this is in our literature. It shows you what's in there, the size of each unit. The size of each configuration, the standard configs, what's in there in terms of boxes, and then raw capacity and what capacity you could get out of it if you had a 3x1 data reduction. So Lots of room in there, lots of things to do. Lots of places to put all of your data and store it and access it. Now, we talked a little bit about scalability. Again, we went to a baseline configuration, and the baseline configurators is what we would sell. That's a starting point. That's the base that you need to have the system and then to use it and get more comfortable with it. Once you do that, you can scale it independently. It's disaggregated. And what that means is you could add as many C boxes as you needed, and you could add D boxes as you needed. In this instance, customer went from a 5U to a 14U. Once he got the system on his platform, started playing with it, started looking at it, and decided what he needed, he was able to add the right pieces to make this a better system to fit their platform needs. So again, I know we've harped on this, but C boxes are for performance, D boxes are for storage. And we're going to have to add switch boxes as you add more boxes to make sure they have enough connectivity to make sure that everything is connected. So what was the system designed for? For Mercury, we're looking at the DoD. We're looking at the DoD. We're looking at any kind of aerospace applications. Of course, energy and rugged commercial. Anything that's in a harsh environment where the rugged commercial needs to be something more than what you can just buy off the shelf. So the platforms, you have some pictures down here that we showed to give a little visual on this. So any of the wide body aircraft, any ship, any subsurface, any energy platform, anything like that, where again, it's more than just a commercial application, something where you're gonna need the ruggedness of it. And that's what we're going to provide. And applications here is pretty straightforward. It's big data. Any big data, AI, machine learning, deep learning, big analytics. So where you have sensors, where you want to capture the data, and where you want to be able to look at that data and process that data right there at the edge. This is a system that'll do that for you. So looking at the summary here, recapping this. So it's rugged, network attached, all flash solution. No trade-offs for performance, capacity, and scalability. It's complete access with low latency at the edge, unmatched security, and it's very, very easy to use. So I think that concludes our slides. John, do you want to take it back? I think we lost John, so I think we're going to go to the questions and answers. I see that there's a couple different questions right now. First question, I guess I would take that. Hey, John, are you there?
Can you hear me now?
Yes, sir.
Do you see
there
me?
You are. Yep.
Oh, excellent. That was weird. So thank you for that. Thanks for jumping in there to help me out, David. I appreciate it. We're going to bring Randy back here too. Our producer's working on that. But before I get started with the Q&A, I would encourage you to go click on the polls and give us some feedback. There's our man, Randy, coming to us as a vastronaut, as he said. And take a look at those polls, give us some feedback, and then also take a look at those handouts. Take advantage of those resources that Mercury and Vast are offering. So let's get to that Q&A. Our first question from the audience, and this one is for Dave. This person says they're interested in learning more about the RDS system and how it can support what they do, but they want to know how soon can they get one and who do they contact? I guess that's a good question.
Well, that is a great question. So to answer that, anybody, Randy has a team of sales, Mercury has a team of sales. I'm available too to talk. I believe our contact information is kind of intermixed with all of this. So if you want to reach out to Randy's team, to anybody in the Mercury team, Mercury does have a very extended sales team, and anybody would be able to help you with that. So how fast can you get a system in your hands? We have them now. We're producing them and getting them ready to hand out. We still are in the final stages of development, but we will have hardware very shortly. Like I said, we have it on hand, but we want to get through our full testing, make sure everything works very well. We're working hand in hand with Randy's team, and that's the best we could do to get something in your hands.
Randy, you want to mention anything about how to contact you or anything on that end, or?
Yeah, absolutely. So my email is very easy. It's randy@vastfederal.com. So feel free to shoot me an email, and we can put you in contact with the right sales teams on that end. You can also go to both the Mercury website as well as the vastfederal.com website.
Okay, and I got a question here from Randy. How can someone know how much compression they will get using your software?
Sure. No, absolutely. So mileage does vary. It is very data dependent. So we do capture a lot of customer data sets, and we have some pretty good numbers as far as backup. Like if you're doing, hey, we're doing backups for VMware and home directories, we have a pretty good idea. But we also have this piece of software called the Probe. And so it allows you to run that against your specific data set, spits out a clear text log file, and gives you that ability to actually see exactly how much compression we'll get on your specific data set. Now, I also know that, sometimes on the DoD side, they don't want to run somebody else's software, dealing with a security operator and things like that. And so I think, looking at the different data sets, we have numbers for synthetic aperture radar. We have data for packet capture. We have data for geospatial and imagery, TIFF images, and certainly RF and other sorts of data ingest. So we have some general idea depending on the types of data and then what the percentages are. So I think that's the other thing. If somebody wanted to understand kind of roughly how much compression we would get, we'd look at the data set, understand if you have some percentages on, we have this much of this type of data, we have this much this, and et cetera, et cetera. We could put a pretty close representation of what we would get on the system.
Okay. And speaking of security, the next question is about security. So what kind of security do the systems offer? And that's a very important question.
Yeah, absolutely. So it is a standard NAS platform. So we integrate with Active Directory and LDAP, as well as other various types of protocol connections. We also have encryption at rest as well as in flight. We have NFS v4 Kerberized. We also support external key management as well. So, we've had this ATO'd at some of the most stringent locations in the federal government. So it gives us the ability to provide a secure platform with both encryption at rest as well as on the fly. And we certainly can dig down that. All of our encryption is FIPS grade, FIPS certified 140-2, and we're going through 140-3 right now. So as they say, we're checking those boxes.
Okay. Next question. This one's for Dave. Is there a situation where one of your customers has purchased the RDS system and did you get feedback on where is it most useful for them? I'm assuming this is from a military customer perspective. Based on
yes, it is, and I'll give you that example to coincide with that. So, one of our recent customers purchased this, and they had to do testing, and they didn't have the ability to capture all this. So they really felt that they were going to have to create something from the ground up. And then because they were the designer of this storage system, they felt that they were then going to have to support it for, 5 to 10 years in the field. And that just didn't appeal to them. So they started looking out in the industry. They found this solution that we're providing, the RDS solution, so they can use it on their rugged platform. So one, it's an existing system. They can then hand it off to their customer, and their customers can work with us to maintain it and to support it. So they didn't have to be involved, but they were the original, designers of this. So they're able to capture more data than they're actually going to produce, which is good. So in this instance, they have a slightly increased D box. So there's 2-3 D boxes in the platform. So they're able to capture all the data that they want. And it's really helped them out a lot because one, they didn't have to support it after the fact. And two, it's a unique solution that they can scale as they need.
Okay. Next question. This one is for Dave too. My company has faced challenges in the past with obsolescence. How long does Mercury plan on supporting the RDS system?
That's a good question. So, obsolescence is always a major issue. So we are dealing with commercial off-the-shelf components. But typically, there's always a roadmap for those, and we have a very robust roadmap ourselves. So as things die out, we're going to be able to replace them and move along. And the nice thing with the vast hardware is, I'm sorry, with the vast software is that as the hardware changes and grows, we're still going to be able to support the older and the newer on that platform. So the obsolescence wouldn't be a problem. We're gonna have again a very robust roadmap to take care of that. And I would estimate anywhere from 5 to 10 years, we should be able to continue with existing hardware. Randy, you want to add to that?
Yeah, absolutely. So, it's interesting. We started, like, when we first started shipping product, a number of years ago, we were looking for the lowest cost flash we could get our hands on. It actually turned out to be M.2 sticks or laptop flash. And so we had these like cool little 2.5-inch drive carriers that would put 5 2 terabyte M.2 sticks, made it hot swappable. It's pretty neat. And so, that was kind of our first box. And so it was TLC M.2 sticks. Basically looks like a gum stick if you're familiar with the form factor. Then we started supporting 15 terabyte QLC flash drives, then 30 terabyte QLC flash drives. These were still in 2.5 form factor. And now we're shipping, like David said, the EL1s from a ruler-based architecture in both 15 and 30 terabyte, dependency or sizes. And we can intermix all that media in the same storage system. And so what this allows us to do is basically grow your cluster with whatever we're currently shipping, right? And so, and the fact that we'll support the flash for a decade, it gives us a lot of flexibility on that. And then to the same notion, we could also intermix CPU inside of the C boxes. And so, we initially were shipping Broadwell and then Cascade Lake, and now we're shipping Ice Lake. And so you can continue to grow your cluster with basically whatever we're currently, shipping on the truck, if you will. So yeah, a lot of flexibility in using technologies and then building a cluster that can span for a really long time.
Speaking of obsolescence, Dave, it also makes me think of COTS, makes me think of open architectures. And I know Mercury as a whole is big on the whole modular open systems approach, MOSA. How does your storage solutions factor into MOSA and open architectures?
Well, it's exactly what Randy said. So we're not MOSA compliant on this system, but it does use the open architecture philosophy. So to Randy's point, as things change, as things grow, the form factors are similar or they're getting smaller. So you'll be able to do that. I think Randy pointed out, or I think Randy mentioned to me a while ago that they had a system, a huge cluster that had some of the first generation, some of the second generation, some of the third generation, all in the same cluster. So they're able to support that hardware. As long as that hardware is supported, as long as the customer is still using it, they don't have to spend the money to upgrade every time something, goes to the next generation, every time the roadmap rolls. So it's definitely a cost savings that way.
Okay. Next question I got is for Randy. Can I use third-party software to help manage my data?
So it's like a trick question, I think. So you can, it's standard NAS protocols, right? So if you're using applications that use NFS or SMB or S3, you can absolutely use third-party software to manipulate the data. I would say from a VAST perspective, if we can solve the cost problem, you really don't need a third party to move data up and down. We support replication as well as a global file system, star replication, multi-site, global namespace. So there's a lot of really interesting things from a software perspective that we've built from a data management perspective. And so we support standard NAS protocols. So we'll support kind of multiple different applications. But as far as kind of moving data, we absolutely have partners that use third-party data to migrate data to VAST. But kind of once it hits the VAST system, you don't really need any software for data migration or anything like that because the system just runs on an all-flash architecture.
Okay, next question from the audience. And this one's unassigned, so whoever wants it can take it. Are there predetermined spares kits for systems deployed in harsh environments? And a follow-up with this, is there also an established failure rate that would determine the number of spare kits needed?
Yeah, that's a good one. So I'll touch on the second part of that, Dave. And
Go ahead.
I think we know, there's certainly spare kits. We definitely So VAST has deployed over 5 exabytes of infrastructure in the last couple of years. And so we have very good metrics on what components fail and at what rates. And so we can absolutely make some predetermined, depending on like, hey, this is, the application, this is how long we want to deploy this system, this is where it's going to go. We can absolutely make recommendations on, the number of spares and what parts actually will need spared kit, right? And so we have predetermined spare kits already, and we do know roughly, again, the more input we get from the customer, the better we can kind of dial that number in. But having so much infrastructure deployed in the data center, it gives us kind of those breadcrumbs to know exactly what the failure rates are of the QLC flash versus storage class memory, switching failure rates, as well as any of the other components on that end.
So to add to that a little bit on the hardware side for the rugged portion, if you look at the design that we have for the D-Box, I'll give you an instance, and that's the back fans. So the fans are usually the first point of failure on most systems, but they're very much required based on the heat, and you need to have the airflow to keep everything cool. But what we did is we designed the fan, each small system of 2 fans, each little block, so that they could be rear removable and plugged in. It's a blind mate. So you're blind mating into the connector there. So if one fan were to fail, one section, you could pull those out and then replace it with a spare kit. Now, it's also been designed, this has been designed that if 1 or 2 or so many fail, the other ones are going to speed up, the other fans that are in there, because there's a definite rack in the back of fans. They're going to speed up and produce the air. So that's what the train of thought that we've done when we've designed this system, and that'll be, so we have the same that we can share with customers of how much when things are going to need to be replaced and what the spare kit look like. Definitely.
Okay. Next question: what's the learning curve for an average systems administrator? Days, weeks for your system?
Yeah,
I think that's probably Randy. Yeah.
Yeah, I can take that one. I mean, I'll give you a good example. I mean, if you look across the DoD, people travel, they want easy systems to manage and support. And that's really something that we pride ourselves on. So I'll give you a good example. We'll take a system cluster, pull it off out of the cardboard, rack it, install the system, and you're up and running in 4 or 5 hours. So the system's very easy to manage, easy to support. As far as intuitiveness, everything that you want to do in the cluster can be done from the UI. So we have a great graphical user interface that allows you to partition out quotas and snapshots and kind of all of your traditional storage type requirements from an enterprise storage perspective. And so, I'm kind of sales guy, like I can manage this system. Right. And so I think that's, kind of I like my crayons, right? Like that's how easy this system is to manage. You can manage it from the UI, but you also have the ability to manage the entire system via command line, or you can automate a lot of this with REST. And so we use a REST API sitting on top that anything you do in the UI, you can also do via REST commands. And we have a system that basically you can pick exactly what you want to do and say, hey, create, and we'll actually create the curl commands to lay down exactly what those REST calls look like. And so we spent a lot of time on the software to make the system very easy to manage and easy to support. Going a little bit deeper, there's no volumes, there's no LUNs to manage. It's just exports, shares, and buckets. And then, your standard administration on top of that, depending on how you want to handle Active Directory or ACLs. We do support POSIX ACLs and things like that. So from an administrative perspective, you can do everything via the command line. You can do everything via the UI, and you can do everything via REST protocols on that end as well. So the system is very easy to manage, easy to support, and most importantly, easy to install, on that end as well.
So let me add a little bit to that, John, if I could, with Randy. So we're going to do the installation. We're going to come, and that's part of what we offer when we sell this. So we're going to come, we're going to do the installation. We're going to have our trained people, a vast trained person is going to be there as well. And we're going to set this up and make sure that everything's running. So when we leave, you'll be able to use the system. It'll be set up and fully functional.
Okay. Just a note to the audience, we still have time for a couple more questions if you want. Shoot them on over and ask Dave and Randy anything that's on your mind. I've got a question here, and this one I'm going to say is coming from me. Dave, what are the most common misconceptions you hear from military users about storage? Is it security? What surprises you at times?
Well, it's the tiering, actually. Everybody's so used to having tiered storage. And I'll give you an example of that. Look at your Outlook, right? You only have so much user space in your Outlook, and then you have to drop everything into your, your archives. And then you have to go in there and search for your archives. So to not have to do that, to have everything at your fingertips, all of your emails and everything. So it's definitely the misconception is that most people believe, or a lot of people believe, that the systems have to be tiered. And that's just not the case. That is completely eliminated with this software in this system. Randy, do you want to add anything on that?
No, I think that was a great thought process. I mean, I think when we talk to folks, especially for the edge use cases, I think they don't think it's possible to both ingest as well as process on the same box. And so for a long time, you've had kind of purpose-built systems. You have a box that gets shipped out there, you ingest a bunch of data, and then you literally sneaker net or fly this box back to CODIS, right? And then upload this data. And then think about how long that takes. And so, having the ability to ingest data, process the data right there in the field. And then, hey, maybe some of that data does have to go back, but you know exactly which data has to go back. So you can do filtering and processing at the edge. And so I think that's probably one of the neater discussions that we have with customers is kind of the art of the possible when you can have an all flash system out at the edge supporting these different applications. And so I think it really comes down to, how customers, want to build a system because we provide a lot of flexibility, and the fact that it's all flash, we just gobble up the IO and give the end users some really great experiences.
Okay. Got a new question here from the audience. Is the system usable for a closed proprietary system?
Not sure that I understand the question.
Military, but you it's more of a military thing, like a closed network within a military, within a unit, within a ship.
From an air gap perspective, we absolutely can support that. So if you just need a box that sits here and supports this, this, and this, we can absolutely support those. A lot of folks would think of those as black sites or sites where you're not going to get your media back and that sort of stuff. We absolutely have customers doing that today. So that's not a problem at all to both support those customers, with folks both from a Mercury and VAST perspective. We do have TSSCI full poly folks that can go on site to whichever sites need that type of air gapped protection and support those customers.
If I could, Randy, we also have processes to get updates to where we're not going to be able to update or you're not going to be able to log in. So we have processes set up to where you're going to be able to put, we'll send it to you in some form or fashion, and then you'll be able to use that in your closed system to update. Say it was on a ship. Obviously, we're not going to be able to get into the ship to do updates, or you're not going to be able to log in. So we have a process for doing those to make sure that everybody's up to date and current.
Okay, and if we're getting close to our end here, where can the viewers, are there any upcoming events where you guys will have your technology on display, maybe at a Mercury Systems booth or a VAST Federal booth?
I'm going to be out in San Antonio, out at DOTIS next week. I know we'll be jointly doing AFCEA West, Sea, Air, and Space. There's a handful of other shows that we're working on together as well. And so keep an eye out on LinkedIn and Twitter. We're constantly promoting the different shows that we're doing, both jointly as well as VAST and Mercury standalone on both sides.
And there's a couple Navy shows there, so some big Navy support for some of your solutions, I would expect as well.
Absolutely. Yep.
Okay. And that brings us right to our time limit today. And I want to thank all of you who came on to watch us and view the webcast. And I especially want to thank Randy and David for speaking and Mercury Systems for sponsoring the event. I'm sorry we couldn't get all of your questions. Someone may get back to you after the webcast with more information. So I want to note that this and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will be archived online and be available for 1 year. Thanks for attending, and I look forward to seeing you on future Open Systems Media webcasts.